Okay, so this is chapter 11. In chapter 11, we're going to take a look at quadratic functions and equations. So I have a page of the book. We are on page 697 of the textbook. Now, for this video, we're going to take a look at section 11.1, which is right in here. Quadratic equations is what we're going to look at in this section. Now, the general form of a quadratic equation is given on this page in section 11.1. Here's what the general shape of a quadratic or general form of the function is, a quadratic function is. So I'll be talking about this in section 11.1. That's what we're going to do. Let me go to my notebook now and let's start. So again, chapter 11, quadratic functions and equations. In section 11.1, we're going to take a look at quadratic functions. Now, the general form of a quadratic function, we're going to take a look at that, is going to be, let's write this one. We're going to write f of x equals ax squared plus bx plus c, where a is different from 0. Again, because if a is 0, the first term here, right in here, this term is going to be 0. So the function reduces to a linear function actually. We no longer have a quadratic function. Now, the quadratic equation that corresponds to this is given by simply ax squared plus bx plus c equal 0. All our equations, we set them equal to 0 before we solve them. So this is what the quadratic equation is. Now, if you recall the ABCs here, these are the numbers, right? ABCs are numbers. And the unknown is x. X would be what we call the variable, or the unknown. Now, an example of this one, let's say, for instance, suppose I have something like x squared negative 3x minus 15 equals 0. And we want to solve it in this section. Now, coming to this section, we already know how to solve quadratic functions. We have not done it in our course yet, but you have seen it in the previous course. You've done it in your previous math class. So the way we done it in a previous course was by factoring it. So if I factor this, it's going to be x minus 5, x plus 3 equals 0. Let me actually change this one. Let me erase this one so it works. I'm going to change that to, let's make it 2x, so it's going to work. I don't want to work with fractions and so on, or radicals. Okay, so suppose we have a quadratic equation like this. Now, remember how this went as far as how the factored form is. To get the factored form, we're looking at two numbers whose product is negative 15, this number right here, and same two numbers need to add to the coefficient on x, which is a negative 2. So in this case, negative 5 and 3 are the two numbers. Their product, these two, the product is negative 15, which is that, and the sum of 3 and negative 5 makes negative 2, which is the coefficient on the middle term. So there we have the factored form. The next step is to solve this by factoring, and according to our zero factored principle, we actually set each factor equal to 0, and from this we're going to say x minus 5 must be 0, or x plus 3 may be 0, and solving for x here, we pick up two solutions, two integer solutions in this case. Now excuse me. Now, factoring is actually a way to do this if the factors are integers. And let me pause for a moment. Okay, so again, if factoring is an option, then we usually use factoring. It's cleaner, it looks better. Now, in this section, we have something called principle of square roots, which is another alternative to factoring for us. So here's how this goes. Let me show you the page of the book where this comes from. and this would be on page 699, right in here. So here's what we call the principle of square roots, which goes for any real number k. If x squared equals k, there's your quadratic equation. It's probably the simplest quadratic equation you can find because there's only one squared term. Then x would be equal to plus positive square root of k, or x equals negative square root of k. So there you go. That's called principle of square roots. Now, this principle works. We don't have to just have x necessarily. So this we have the more general form of the principle of square roots, which is on the next page. And there you go. This is a bit more general. And for this one now, it's probably the same layout, but the difference is used to be little x, now it's cap x, where cap x here could be any expression, any algebraic expression. So that's what that is. So there you have this one. Now, let's take a look at something here real quick to show you. In here, I'm going to actually show you how that principle works. So this is again, this would be the principle of square roots. And again, the way the principle works is goes like this. If we have x squared equals k, then x would equal to plus or minus, and then we have square root of k. Now, some think of this as taking the square root of both sides of the equation, which is okay. The thing that's important to note is the following, is that we have to have plus or minus in front once we do this principle, okay, which picks up two solutions to that equation. Now, to give you some examples of this one, of the principle, let's say I have something simple, x squared equals to 9. So based on the principle, I can take the square root of both sides, and taking the square root, you get plus or minus. Again, the moment you take the square root, you have plus or minus. And then we have square root of 9, and of course the square root of 9 is going to be plus or minus 3. Another example, because we said k, then the constant here, k, could be any real number, so I'm going to choose a negative number now. And here again, x is going to be equal to plus or minus, and then we go square root of, this time, negative 9. Now, if you recall, square root of negative 9, we can write it as root 9i, and that's because I is equal to square root of negative 1. This comes from chapter 10, the last section of chapter 10. That's what we did when we talked about complex numbers. So from this, we can actually finish this, and we get two imaginary solutions, plus or minus 3i, the answer to this one. So there's the example. Now, the general form of the principle of the square roots tells us that the expression in x could be any expression, doesn't have to be just x. So for this one now, I'm just going to be different. I'm going to call that m minus 5 squared equals to 7. So using the principle, we're going to take the square root of both sides, and when we take the square root of both sides, we have m minus 5 equal to, and then we go plus or minus again, and here we have root 7. And to solve this one, the next step is to add 5 to both sides, and that makes this 5 plus or minus root 7, and that will give us two irrational solutions to that quadratic equation. Two irrational. The reason it's irrational because here square root of 7 right in here, square root of 7 is going to be irrational, which makes the roots or the solutions irrational for this one. Okay, now so that's good. We'll take a look at some homework problems in a few minutes. Now, the other idea in this section that we're going to look at, it's called completing the square method. Okay, completing the square method, which is another method for solving quadratic equations. Now, before we actually look at this idea, so let me write it. Our next idea is this. We're going to look at or talk about completing the square method for solving quadratic equations. Now, again, before we look at it, let's take a look at these expressions for the moment. Okay, so let's say I have something like x plus 7 squared, and we want to expand this. Now, one way we can expand it is to write it as repeated multiplication. By definition of exponents, we can write x plus 7 squared as x plus 7 times x plus 7. And then we can FOIL these. When we do, this is first, outer, inner, and product of last, which is 7 by 7, 49. So what I did just now was this one. This would be the F. This would be the O. Okay, so that's first, that's your x squared, and 7x. And then I did inside and outside terms. Okay, and there's your FOIL, and that's how I got these numbers. Okay, now if I combine like terms on the right side, I get x squared plus 14x plus 49. Okay, so there you have it. Again, something you've done before, nothing new for us. Now let's take a look at x minus 11 squared this time. So again, expanding the binomial, we're going to get x squared. Negative 2 times 11 makes 22x, and plus 11 squared is 121. Now, the reason I have this negative 22x in the middle is pretty much the same as the reason you have the 14x here. So if you look at this one now, the 14x here, you can see that that's when the O and the I combine to 14x, which another way to do this is to actually take twice x by 7. That makes it 14x. And here's the justification for it. The FOIL is the justification for that. So that's exactly what I did here. Instead of foiling it, I did the first one squared, got x squared. And then second one, negative 11 squared, gave me 121. And then twice first by second gave me negative 22x. So there we have this one. Now, these expressions that we have, this one and this one, these are, if you look at the general form, the structure of this expression, these are both quadratic expressions, okay, which fits our work for what we're doing. Remember, up top here, we're looking at quadratic functions and equations. So both of those look in this form, what we just have down here on our page. Now, oops, sorry, went a little fast there. Okay, now these quadratic expressions, we call these perfect square trinomials. Well, trinomial because there are 3 terms, 1, 2, 3. So these are called perfect square trinomials. Now the reason it's called perfect square, you can think of, in the case of, for example, x minus 11 squared, you can think of a square whose sides are x minus 11 by x minus 11. So in that sense, we get this perfect square that we are looking at here. Okay, so that's just the name behind, the reason behind the name, the terminology. Now, so now let's do this another way. Suppose now this time, let's say I'm going to give you a trinomial which is incomplete. So let's say I'm thinking of x squared plus 10x. And we're going to have a missing constant here. Okay, so right in here, I'm missing a constant. Now think about this. If we were to make up our own number, a constant, what would you pick so that this expression is going to become a perfect square trinomial? And we're talking about, sorry about this, we're talking about this expression. We want this to become a perfect square trinomial just like these. Now, if you go back to looking at the relationship between the numbers, like the 14, the 49, and the 7 here. Well, half of 14 is what 7 is. And if you square the 7, you get the 49. Looking at this other example, you look at half of negative 22, that's negative 11. And then you square negative 11, it becomes 121. So if we draw on the same experience, on the same what we just did, then we can argue that, well, the number that we need here is going to be, half of 10. So I'm going to write that now. So the number is going to be 1/2 of, means multiplication, of 10. And that will make it a 5, right? And that's pretty much the number that's going to be in parentheses. So here I'm going to write equal to x plus 5 and then squared. And the constant, remember, is going to be when you square the 5, that's what the constant is. It's going to be the square of the 5 that goes in here. So that constant is going to be 5 squared, which is 25. So that's what I'm going to write here, 25. And what we have in here, this expression is what we call a perfect square trinomial. And this will be the binomial form of that. So this process of adding the number, the highlighted number, it's called completing the square method. So we had an incomplete trinomial, and by adding the appropriate constant, the proper constant, we turned it into a perfect square trinomial, which is up here. That's perfect square trinomial. Okay. So now let's take a look at an example of how we can do these in our exercises. And let me pause for a moment. Okay, so I'm back. So let's take a look at some exercises here, and we're going to take a look and see how we can do what we learned in this section. So I'm going to go to page 706. And sorry, I took my keyboard off so I can write on the screen here. That's why I have to use this keyboard. Okay, so here are the exercises on page 706, section 11.1. Now, for your homework, here's what I have, which is on the homework document I've sent you in the beginning of the semester, and it's on Canvas also. So let me write down your homework problems. Your homework, you're doing exercise number, this is section 11.1. You're doing exercises numbers 11, 23, 41, 53, and 65. So those are the ones you're looking at. Okay, so I'm going to actually work problems that are very similar to these. Okay, so in actually section 11.1, you're doing number 11. Okay, so you're doing this one. Let's take a look at number 12. Now, the way the question reads here, the question reads, solve, find all complex number solutions. Now, this is the principle of the square roots. So we're going to solve by principle of the square roots, not by factoring, even if it's factorable. So let's take a look at exercise number 12. In number 12, we have 4y squared equals 12. So exercise number 12, right in here. This is exercise number 12. We had 4y squared equals 12. Okay, now one thing we need to do before we can use the principle of the square roots, we want to make sure that the variable that appears in the squared form is isolated. That means it's by itself. No numbers multiplied by it. It's not divided by anything, and nothing is being added or subtracted from it. So that means I need to do the following. I need to divide both sides of this by 4. And when I do, I get y squared is equal to 3. It's pretty simple, huh? And then the next step is to apply the principle of square roots. That is by taking the square root of both sides. And remember, the moment you take the square root, you have plus or minus here. So I'm going to have plus or minus square root of 3. And there we solve that one. Pretty simple when you use the principle. Let's take a look at another example. That was number 12. The other one you're looking at is number 23. So let me kind of show you what number 23 now looks like. This is exercise number 23. And there you go. In number 23, that's this one. The one you're doing for your homework is this one. So I'm going to do number 24. Number 24 is y minus 4 squared is equal to 18. Okay. Number 24. Number 24 we have, again, it was y minus 4 squared equals 18. Now, again, because we have this squared on an expression, we can proceed with the principle of square roots. So that means we're going to take the square root of both sides. And when we do, we're going to get y minus 4 equals plus or minus, and then here we're going to look at, I don't know what happened. Okay, plus or minus square root of 18. Okay, now we can add 4 to both sides to isolate the variable. And also square root of 18, we need to simplify square root of 18 like we did in chapter 10. So 18, I'm going to think about two numbers whose product is 18. The right numbers are 9 and 2, right? 9 by 2. You can also think about 3 by 6, but 3 and 6, neither are perfect squares. So that's not what we want to do. We want a number that we can multiply by itself, a repeated number, if you will. That will give you one of the factors, namely the 9 here. Okay, and you can see in the next step, the reason for that is now we can take the square root of 9 and it becomes 3. And then we have square root of 2, and there you go. We have 2 irrational roots of this. 2 irrational. Now they call them roots or solutions, so we're just going to use that terminology. We have 2 irrational roots to the quadratic equation. The reason it's irrational is because the square root of 2, right? And here the square root of 2 is irrational, which makes the nature, the type of solutions irrational. We look at the types of solutions in section 3 when we go to section 3. Okay, so there you have it. That's the exercises that you see on that page, which involve the square root, the principle of square roots. Now, let's take a look at exercise number 41, which is a little bit different. Now, in number 41, and we're over here now, it's called completing the square. Now, for this one, the instructions read, replace the blank in each equation with constants to complete the square and form a true equation. So if you note here, again, you're doing number 41, you're doing this one. So we'll do one like it, like these. If you note here, the constant is missing. And of course, the square of a binomial, the constant here is missing. So we're going to go through and actually do number 42 now. So you see how we can say replace, complete. Okay, so we're not going to solve it. We just want to complete the square, number 42. So let's take a look at that one. And maybe we do another one after that. We do 42 and then we do number 44 also. These other ones involve fractions, so I can do an example of these if you want, but these are again a little bit more involved. Not that they're difficult, it's just anytime we talk about fractions, things kind of get in the way. So anyway, I'm going to do numbers 42 and 44. So let's take a look at number 42. In exercise number 42, the expression is t squared negative 6t equals, and then here's t minus something squared. Okay, now remember the process how we did this. The number that goes in here, let me highlight it. The number that goes in here, the constant, is going to be what? It's going to be half of this number. So it's going to be 1/2 of negative 6. True? And that makes it negative 3. And then we're going to square it, right? So negative 3 gets squared, and that becomes a 9. And that's what we're going to add here, a 9. When you add a constant using completing the square, you're always adding because of the squaring effect. Okay, so we're going to add a 9. And the number that goes actually in here now, it's going to be simply whatever the half of negative 6 is, which is again negative 3. So it's going to be minus, and it's going to be, there you go, that's negative 3. Again, the reason it's minus is because negative 6, that's negative. Half of negative 6 would be negative 3 for that reason. Okay, and there you go. We're done with that exercise. That was number 42. Now, if we take a look at number 44, in number 44, we have this time is x squared plus 2x. And we want to know what we need to add over here to turn it into a perfect square trinomial. Remember the procedure. We're going to go 1/2 of this number, right, which is 2. So we're going to go half of 2, and that's going to be 1. But then remember, we need to square this number. So we're going to go 1 squared, and of course 1 to any power is 1. So what we're going to add here is 1. The binomial form of this is going to be x plus 1 squared. And there we have completed the square in this one. So hopefully you're comfortable with completing the square with an expression. Now let's take a look at the other exercise that we're doing. This was number 41 and 43 we did. We did 42 and 44. So we did these. We did 42 and then we did number 44. Now, let's take a look at exercise number 53. Scrolling down here, and this is number 53. In this exercise, we actually want to solve now. So if you read this, it says solve by completing the square. Okay, so solve by completing the square. This is, again, we're doing number 53. I'm going to do number 54. Okay, and then we do another one. We do number 58. So we're going to do 54 and 58 together. Okay. So first in exercise number 54. This is number 54. In that exercise, the expression is t squared negative 4t, and then they say this is equal to negative 1. Okay. Now, remember, we need to create a perfect square trinomial first. So that means we need a constant here. And if you recall again, that constant is going to be half, right? It's going to be 1/2 of negative 4, whatever that is. Half of negative 4. And that's negative 2, but then we square it, and that becomes 4. So what goes in here is plus 4. Now, we need to add 4 to the other side to maintain the balance or the equilibrium of the equation, right? We have an equation. So anything we do to the right side, we got to do to the other side, to the left side. So that's what we did. Now, at this point, let's see. On the left, we're going to exchange these 3 expressions in exchange for t minus 2 squared. Now remember the negative 2 in here, this negative 2, where does that come from? That's again the same as, it's the same as this number. Okay, so that's whatever that is, you put it in parentheses. And do not forget to square it, otherwise this will not be correct. Okay, and that's going to be equal to -1 plus 4 is 3. And now we have created something that looks no different than, let's say, your exercise number 21, the one that's for your homework. Okay, next step, I'm going to use the principle of the square roots, correct? In order to isolate the binomial. So that's what we're going to do. We're going to go t minus 2 equals, remember, we need to have plus or minus the moment we take the square root, and we put 3 here. And then we have t is equal to 2, and of course we have plus or minus square root of 3. And that will give us, again, 2 irrational solutions. Once we have 2 plus that, the other 2 minus square root of 3. Now, we don't need to reach for a calculator and actually find the numbers. As long as we can give them the exact value and solve it, that's all we're after. And there you have it. This would be, this equation is solved using completing the square method. Let's take a look at another one. In this next one is number 58. In exercise number 58, the expression is t squared plus 6t negative 5 equals 0. Okay. Now, for this one, again, even if the equation is factorable, we want to do it by completing the square method. So, let's take a look at how we're going to do this one. Now, in number 58, notice we're given a negative 5 here, right? That's this negative 5 is right in here. This is negative 5. So when we start these equations, we don't need the constant that's on this side. Okay, we're going to create our own constant. Remember, we're going to create a perfect square trinomial. So what I'm going to do first, I'm going to move negative 5 to the other side. That's going to become 5. Or you can think of adding 5 to both sides of the equation. Now, next step, we go through our routine on the left side. Remember, what we need to add is half of 6, correct? Oops, sorry. I don't know what happened here. And I know what happened. I used the mouse. I'm going to use a pen. Okay. So, right in here, what we need to add is, again, half of 6, right? And then we actually come up with 3. Remember that number? That goes here. Half of that. But then don't forget to square it, right? So we're going to go 3 squared, and that's 9. So we're going to add 9. We're going to add 9 to both sides. And again, on the left side, we're going to trade 1, 2, 3 items for square of a binomial. And inside parentheses, we have t plus 3 squared equals 14. And again, where does that 3 come from? That would be whatever half of the coefficient on middle term is. The middle term being 6t. Okay. Now, next step is to use the principle of the square roots. So I'm going to do that. I get t plus 3 equals, and then we have plus or minus square root of 14. And the final step, we're going to subtract 3. And we have plus or minus. Now, square root of 14, there's nothing we can do with that because there are no perfect square factors in 14. 2 times 7, neither 2 nor 7 are perfect square factors. So that's going to be the solution. Again, we have 2 irrational solutions in this one. The solutions could be complex, like if that was, let's say, for example, I'm just making this up. Let's say if it was negative 14, the radicand, this becomes root 14i, and there you go. So this is what's going to be instead of what we have here. That's if the radicand is negative. Remember, we now handle those through that imaginary unit I, where I is square root of negative 1 by definition. Okay? And there you go. That is number 58. Now, the one last thing about this section, and we're done with this section, is there's a little string attached when you use completing the square method. So actually, there you go. I have all three of them here in front of me. Now, if you look at the coefficient on the squared term up here, number 44, and then in number 54, and in number 58, if you look at these coefficients, every one of these coefficients is 1 because it's not written. So here's a 1, there's a 1, and here's a 1 here. Now, it's imperative that the coefficient on the squared term has to be a 1 when you complete the square method. It's because the way we go about it, half of the middle term squared and so on. So, what if that coefficient is not a 1? Which brings us to exercise number 65. So let me again go to the page of the book. And we're going to take a look at on the following page, page 707. That's where we have one of these types. So top of the page, once this thing loads, you're going to see solve by completing the square. Now, if you look at these numbers 65 through 70, the numbers in front of the squared, a 9, a 3, a 5, 4, 2, 4. Every one of these is different from 1. So, now there is a hint, actually, in the statement of the problem that reads, remember to first divide. So that's how we're going to remedy this coefficient being other than 1. So let's take a look at, again, you're doing number 65, you're doing this one. Let's take a look at number 66 for our work on our notepad. Okay, so in exercise number 66, that's the one we're going to look at now. Number 66. Okay, exercise number 66 reads 4x squared plus 8x equals negative 3. So again, just to point out, this coefficient is not 1, different from 1. So our first step is to divide everything throughout by a 4. So that's what I'm going to do indeed. We're going to go by 4, and even on this side, we're going to go by 4. And here we go, my goodness, we have fraction on the right side. Now, divide everything by 4. So on the left, we're going to have x squared plus 8 by 4 is 2x. And of course, here we have equal to 3/4. Now, notice I created a space here right after 2x because I'm getting ready to add a constant. Okay, so, and keep in mind our routine, we're going to add half of the coefficient on x, namely a 2. Remember, half of that number. And that's going to be a 1. But we're going to remember to square it, right? 1 squared, and although that's going to remain as 1, just want to emphasize we do square it. And that's what's going to get added right in here, right? And we're going to add it to both sides. So we're going to add a 1 on this side, and I'm going to add a 1 on the other side. So to the left, now I'm going to get x plus 1 squared. And on the right side, I'm going to add 1 3/4. And sure enough, we're going to get 1 3/4, right? Here's 1 3/4 as a mixed number. But I can write it as, let's see if I multiply. I'm sorry, I messed up my 4. There you go. I'll fix that. Sorry. So if I fix this one up, it's a mixed number format, right? I can write it as an improper fraction. Remember how that goes. You go 4, multiply 4 times 1 plus 3. So it's going to be 7/4. And I'm going to write 7/4 on the other side. And now we are in a position to apply the principle of square roots, and that's what I'm going to do next. I'm going to take the square root of both sides, and that's going to make it x plus 1 equals plus or minus square root of 7/4. That's taking the root of both sides. Our next step, we're going to isolate x. That means we're going to subtract 1, right? And then I'm going to have plus or minus. Now, let me work the square root of 7/4 here so we don't have to rewrite that whole equation 2-3 steps down. So I'm going to break this into root 7 over root 4, and of course root 4 is going to be what, 2? Oh, sorry, that's root 7. Let me erase. And so the top's going to be, sorry, it's going to be root 7 over square root of 4 is 2. So it's going to be just that. And here again, we have two irrational solutions for this problem. And this is what completing the square method is. So if the coefficient again is not a 1, such as the one we did, if this coefficient is not a 1, if it's a 4 or whatever, we divide it by that number throughout, both sides. Now sometimes this works out nicely, other times you may introduce fractions and so on, but as long as we can just get an idea how to do this. But anyway, we did an example of it. Hopefully now you should be able to do exercise number 65. And with that, we are done with this section. Okay, and I'm going to stop the video now. Thank you.